Hey, hey, it's Dr. J. I'm back with some more calculus. Today, rates of change instantaneously. So the last time we were together, I went over how to find the average rate of change. So let me just review that very quickly in this example. Recall that the average rate of change is the same as the slope of the secant line. Through any two pairs of points. So I prepared this graph ahead of time so that you wouldn't have to sit here and watch me create the graph like I did with the previous tables, which can be exhausting to watch somebody fill them out. So I got this one all ready to go. And what we're going to do is do the average rate of change through several different intervals. So let's do -4, f of -4, and 4 f of 4. So we'll start with a pretty big spread. Got to scoot over a little bit. Get me out of the way here. So we have -4 and f of -4. So this point here will be -4 and -2.5. And then we'll go all the way to 4 and f of 4, which will be 4, 3. So that'll be our first secant line. My ruler is going to be long enough to make it all the way there. It's not perfect, but you get the idea. I'm going to need a bigger ruler. I've got one in my office. Anyway, you get the idea, right? So this is a secant line through these 2 points. And let's go ahead and find the AROC. So we got the slope of the secant line. I'm going to call this, I don't know, M1. Because that's my first slope that I'm calculating. I could call it AROC 1 as well. But remember, AROC is the same as slope. So we got 3 minus -2.5 over 4 minus -4, which is 5.5 over 8. As a fraction, that's 11/16. I'm just multiplying the numerator and the denominator by 2 to get a nice fraction. If I divide this on my calculator, you might not be happy with what you get. And it's a little bit tricky to see the pattern when you, but let's go ahead and do it on a calculator. 5.5 divided by 8. It's not that terrible. Yeah. So as a decimal, it's 0.6875, or as a fraction, 11/16. Yeah. I like exact values whenever possible, so I'm going to go with that one. All right, let's do a few more. Let's do -2, f of -2, and 4 f of 4. So when we're trying to find the instantaneous rate of change, we fix one point. And we let the other points get closer and closer and closer so that we can use calculus. In particular, we can use a limit to find the values. So let's go here. So it looks like we have -2 and -3 is the y value here. And then this is still the same point 4, 3. So our slope, we'll call this slope 2, is, I don't know if you can see that very well. Let me switch back to black. So I got 3 minus -3 over 4 minus -2, which is 6, which is 1. Well, that's easy to draw. A slope of 1 is a perfect diagonal through every box. Just goes through the corner of every box until I arrive at this point. So that's M2. And what we're doing is we're going to look for a pattern. As the slopes get closer and closer to this point, the average rate of change will get closer to the instantaneous rate of change. So in order to find the instantaneous rate of change, we're essentially going to take a limit of the average rate of change. Average rate of change is plural. We're going to do multiple of these to get there. Let's do one more, or maybe 2 more. I think I've got room for 2 more. Let's do 0, f of 0, and then we'll keep the second point fixed again. Get closer and closer to it. So my next one is here. So that's 0. Oh, it's another -2.5, and then 4, f of 4. We know f of 4 is 3. So we'll call this M3. It's our third slope. I'm just going to kind of freehand this one. That's our M3. So that's going to be 3 minus -2.5 over 4 minus 0, which is 5.5 over 4. Which again, if I want a nice fraction, I just multiply the top and bottom by 2, and I get 11/8. It's kind of neat when you leave this as 6/6, right? You kind of see the pattern here. You kind of see what's happening. The numerator and the denominator are changing, and then they're going to get closer and closer to one particular number. We'll get a pretty good idea about what it is on our next one. So for our next point, let's go right here. Let's do 2 f of 2 and then 4 f of 4. So I've got 2, -1, and 4, 3. We'll call this one's going to be very hard to draw. Sort of hugs the graph very, very closely. That's going to be our M4, our fourth slope in the sequence. And then we'll take a limit and see what it's approaching, and that will be our instantaneous rate of change. So we got M4 is 3 minus -1 over 4 minus 2, which is 4 halves, which is 2. So you see what's happening is we have our M1 was 11/16. Our M2 was 1. Our M3 was 11/8. Our M4 was 2. So we're looking for a pattern as to what's happening next when we take the limit. That's what we're kind of going for here. So this limit of the slopes of the secant line is called the slope of the tangent line. And it's not too terrible to see on here. It's not too difficult to see it on here. As these lines are going like this, you see the sequence. So this is 11/16, and then this one was 1, and then this one is 11/8, and then this one is 2, right? And then the next one will actually be 11/4 if I did the next one. So the sequence is going to go 11/16, 1, 11/8, 2, then 11/4, right? If I did M5, I'm going to spare you the details, but the next one would be 11/4. And that is so close. If you draw this line, 11/4, think about what that means. That means it's going down 11 and over 4, right? So it will look so close to the tangent line. The tangent line only touches the graph at one point, in particular 4,3 for this graph. And so I predict that, I dropped my pen. I'm predicting that the slope of the tangent line is equal to 12/4, which is 3. So as I get closer and closer and closer to this point, this sequence of numbers is going to go 11/16, 1, 11/8, 2, then 11/4, and then, well, it'll just keep getting closer and closer and closer to 3. Right? So the limit is equal to 3. All right. Now, it's very difficult to see with this sort of messy graph here, but if I sort of erase everything except the tangent line, if I just draw the tangent line here, you can see that the slope is approximately 3. Pretty darn close to 3. All right, so it's very difficult to see that on a messy graph, but if I did it very cleanly, there's 4. Sometimes I'll give you a much cleaner version of this. And then the slope is like this. There's the tangent line at 4. X equals 4. And now it's a little bit easier to see. I remember the graph was like this. Kind of getting off topic here, but when you look at that messy graph, it's very difficult. I'm just going to do it very quickly. So there's the graph I erased very quickly. The tangent line only touches the graph at one particular point. And if you look very carefully, and on your homework you'll be able to zoom in, you could look here at this slope and just take it to the next whole number here. So the slope of this line is 3 over 1. Yeah, so the distance here is 1. And so I'm just sort of verifying, check. Once you get rid of all those other lines, it's a little bit easier to see what's going on. So that's where we're at today with instantaneous rate of change. Now, we would like to have a more precise way to do this, right? We don't want to have to, or you don't want to have to sit here and watch me draw all these graphs. And I will draw graphs from time to time, but wouldn't it be nice to use the algebra that we've been learning this whole time and the limits and what have you to be able to calculate the instantaneous rate of change as a limit? So, example 2. Without a graph, sometimes we call this doing it blindly. Can't really see the graph, but probably not a very big surprise that this graph will look very much like the graph you just saw. So before I turned on the camera, imagine how long that would have taken if I would have had you watch me draw the entire graph. I've tried that before. It's exhausting. So this is a similar type, it's not exactly the same, a similar type of function that would have created the graph that we just did. So in order to make it a little bit more streamlined and a little bit less sort of, guessing and checking and kind of clumsy the way it was in the last example, wouldn't it be nice to use some algebra? So let's just generalize what the average rate of change would be on the interval AB. So think of this as your X1 and this as your, they're closed interval. This is your X1 and this is your X2. I'm glad I corrected that because with the parentheses there, it wouldn't have meant the same thing. So this is the closed interval AB. So what is the AROC? It is f of B minus f of A over B minus A. Right? It's the same formula. It's y2 minus y1 over x2 minus x1. But now we have a specific formula. So when we plug in that formula, we plug in these values to that formula, this is what we get. 3b squared minus 4b minus 6 minus, I like to have an extra set of parentheses, 3a squared minus 4a minus 6 all over b minus a. Now this basically represents one of those fractions we just had in the graph, but it's a little bit cleaner. I don't know if you think this is cleaner, but watch, it'll get cleaner. Right now it looks kind of messy, but I can clean this up nicely, distribute that negative. That changes the signs. I could do some canceling. I got a -6 and a +6. I'm also going to do some grouping. All right, so this is the slope of one of the secant lines, right? So this is not instantaneous yet, this is average still. So in order to find the instantaneous, I need to simplify this, and then I need to look for some kind of a pattern, right? As the limit approaches, in this case, what will happen is B and A are going to be getting close to each other, right? So we're bringing the 2 points, like in the graph, closer and closer and closer to each other. I don't quite see it yet. I don't know if you can see it, but it's we're going to do a little bit more cleanup here. So let's take the first group and factor it 3b squared minus a squared. That'll be this first group. And then we'll take the second group. We'll factor them. This one's a little bit easier. I'm going to pull out the negative and the 4. And I'm going to get b minus a. And then this is all over b minus a. I'm running out of space, so let me just copy this one more time. B squared minus a squared minus 4b minus a all over b minus a. One more factoring. Hopefully you remember this special recipe. B minus a, b plus a. I also like to write the denominator twice. That's an important trick, or technique is a better word for it. I usually wait till the very end and I write the denominator out twice, and that prevents me from false canceling. False canceling is like early in the process, you cross something off that doesn't really cancel. The only thing that cancels early in the process are the 6's in this example, but everything else cancels right here at the very end, and now you have your slope. Which is much easier to understand. As a slope, it's 3b plus 3a minus 4. Now, without doing a super detailed graph, let me explain what this means. This is the point A, f of a. And then this is the point B, f of b. Now, remember how long it took me with the graph to go through every single possible pair of points. The AROC is the slope of this line. Yeah, the slope of this secant line. Right? Well, now I have the slope right here. It's 3b plus 3a minus 4. So think about it, had I done this first, and this is just the story of my life and the story of my approach to teaching is I don't want to tell you it before you see the details. I want you to see the hard way first. And then you go, oh, that's exactly what we were just doing with the last problem. Now, of course, these numbers are going to come out different, but you can kind of see what would happen. If this was, I don't know, what did we do? 4, comma 3, yeah? And this was, I don't know, negative 2, comma, what was it? Negative 2.5 or something. I don't know. I'm just making these up at this point. Here, let me not make them up. Let me just say 4, f of 4, and then I don't have to make them up. I'd rather not be making up a number that's not right. Because it turns out it really doesn't matter if all that matters is the B and the A, right? I mean, you could say, oh, it doesn't matter what these Y values are. Well, the Y values were determined by the function. So it's not that they don't matter, but they are dependent upon this particular example. So for this particular example, these Y values, I don't want to say they don't matter, but they've already been resolved in the equation. And so what this tells me is that if this is negative 2 and this is 4, then my slope is 3 times 4, because that's B, plus 3 times negative 2, because that's A, and then minus 4. So 12 minus 6 minus 4, so the slope was 2. For this particular graph, it's very similar shape to the one I did in example 1, but the idea is that once you have a formula for the average rate of change, now you can adapt it to any of the examples as they come along. All right, so that's the first version of the AROC over an abstract or arbitrary interval. We're basically going to do 3 or 4 different versions of this to kind of really see all the different sides of it. Let's take a different function. Not too much different, but just something a little bit different. How about x squared plus 7x plus 8 on the interval a and a plus h. So instead of going from A to B, what we're doing is we're taking the same basic structure, and I'm going to have to erase this in a minute, but I'll just show it here. Instead of calling this B, we're calling this A plus H. There we go. So you're going to see that the calculation is going to be very similar, but we won't have the letter B. Instead of B, we'll have A plus H. Now this one can be a little bit messy, so let's do everything very clean, or as detailed, or as clean, I guess, as I can keep it on this board. So I have f of A plus H minus f of A all over A plus H minus A. So that's going to be A plus H squared plus 7A plus H plus 8 minus, don't forget the second set of parentheses, A squared plus 7A plus 8 all over H. So these guys will cancel early. That's fine. A, negative A. So you could do some early canceling. If it's adding and subtracting the same number, then go ahead and cancel that. However, if you see dividing and it looks like you can cross them off, don't do it until the very end. All right. You can do it at the very end, but if you try to cross things out now, you'll, like, for example, I've seen people cross off the A plus H's because one's on top, one's on bottom. Resist the urge to do any quotient canceling. You can, adding and subtracting, that's okay. You know, that's legal. All right, let's clean this up. So that's going to be A squared plus 2AH plus H squared plus 7A plus 7H plus 8. Distribute this negative A squared, negative 7A, negative 8, all over H. Now be careful here. If you need to review your algebra, this is not the time to do it in the middle of my video, but I will just mention, maybe I'll do one of those clouds, algebra review. A plus H is AA, AH, HA, and HH. Yeah, you guys remember basic multiplication, also known as FOIL. There are 4 terms. There's the first, the outer, the inner, and the last. So that's A squared. You have 2 AHs. And you might go, well, one of them's an HA and the other one's an AH, but the commutative property says that the order doesn't matter. And then you have an HH, which is an H squared. So that's your 10-second algebra review. You can also do some additive canceling. So negative 8, positive 8, negative 7A, positive 7A. negative a squared, positive a squared. So that's called additive canceling. Don't cross off any h's yet. Until the very end, and watch very carefully how I do it. A lot of different presentations will show this different ways. I like them all, but this is my favorite way. In the last example, I said to write the denominator twice. In this example, because there's 3 terms, write the denominator 3 times, and then cancel all 3 times. And keep in mind that h squared is hh, kind of like I wrote it over here. I think that's an easier way to understand canceling unless you're already an expert in algebra. I mean, hopefully you're all moderately good at algebra. Probably wouldn't be taking a calculus course, but I know for myself and for many students, you actually learn algebra the best and the most comprehensive algebra when you're in a calculus class. That's when it really matters. So there you go. 2a plus h plus 7. Now watch how cool this is. We don't know what a or h is, right? But our goal is to shrink the size of the interval, just like we did in the first example with the graph. So we have a sequence of lines that are getting closer and closer and closer together. Yeah. So as we move along, h is going to get very, very small, and then a will become some particular number. So watch how nice this is to switch to example 4. Same question, just change this to a number. How about -3? Now, I did all the math already. So all I have to do is plug in -3 for a. And I don't know what number you're going to get. You might get -3. You might get -5. You might get 2. The a will change, but this slope is a recipe for this particular function. Now, if the function changes, obviously you have to do this math again. But then you just plug in a. This is a new example now. So this is the answer to example 3. Yeah, 2a plus h plus 7. In example 4, I'm being very specific with it. I'm plugging it in. 2 times -3 plus h plus 7. -6 plus h plus 7. So that'll be h plus 1. -6 and +7 will be 1. And if you like to see an abstract, again, I'm not going to break out the grid and the graphing board because it really will take a very long time. But generally speaking, what's happening is over here at -3, we have some point. I don't know, what is it? F of -3 would be, and I said earlier, it doesn't really matter. You could just put a dot and call it F of -3, but I'm just curious what it is. It would be 9 minus 21 plus 8, so it would be -4. Right? Yeah. 9 plus 8 is 17. 17 minus 21 is -4. So there'd be a parabola like this. Again, I'm not being very detailed. It's a terrible drawing, but you get the idea. It's just your average everyday parabola. They all basically look the same. I mean, some of them are wider and skinnier, some of them are upside down, but the basic shape is the same. So what does this answer represent? This is the slope of the secant line connecting -3, -4, all the way to, let's just pick a random h here, -3 plus h, where h is the horizontal distance between these 2 points. So the slope of this line is h plus 1. So if h is very small, so as h gets very, very small, it approaches 0, the slope of the AROC becomes closer and closer to the slope of the tangent line. Yeah, which we call AROC, instantaneous rate of change. All right, I guess we should just do another example. Let's use some different numbers. Let's say f of x is 5x squared plus 6x minus 9. Let's find the AROC on the interval 4, 4 plus h. So I will just make a little side note based on what we just did. A is 4. You can plug it in now, or you can wait. It's up to you. So the way I did it in the last example, I did all the calculation with A, just the letter A, and then when I was done, I plugged in 4. Right? I kind of like to do it that way. So I've got, it's helpful because you might not have the same number that I have, right? So if you do it with an A, I just think of A as any number, and then my example has a 4, but your example has a 3. Well, just do exactly what I did and then plug in 3, right? So it's a little bit more, flexible with the values. So much of this is going to look almost identical to what we just did. My hope for you before the chapter 2 test is that you can do this, I don't want to say with your eyes closed, but metaphorically with your eyes closed. Of course, you should have your eyes open while you're doing it, but you're not really needing them. So this is going to be 5a squared plus 2ah plus h squared. That sounds familiar. Last time we didn't have the 5, but that's okay. We can adapt. Distributing this negative, you should always be very careful there. Changes the signs of these last 3 terms. And then I'm going to distribute the 5, which we didn't have in the last example. A lot of writing. A lot of duplicating stuff. all over h. Eventually, I'm going to write the h more than one time, but let's just clean it up a little bit. So I've got 5a squared, negative 5. Hey, that sounds familiar. That happened before. Negative 6a, positive 6a, negative 9, positive 9. That's always going to happen, right? All of the a terms will cancel, and the constant terms. And so all of the remaining terms should have an h. So let's just put our answer up here. It's going to be 10ah plus 5h squared plus 6h. And then I'm going to write the denominator 3 times. And cancel. So my AROC is 10a plus 5h plus 6. And so now I'm going to plug in a equals 4, which I could have done that earlier in the process. Right? I want to make that very clear if you're watching. I could have put the 4 in everywhere there's an a. It would be very messy, but I could do it. I think it's cleaner just to wait till the end. Then you only have one a, as opposed to look how many other a's you had. A. Look how many a's that is. You wait till the very end, there's only one. You plug it in, you get 10 times 4 plus 5h plus 6. So that's going to be 46 plus 5h. I don't care what order you write it in. You could also write it 5h plus 46. Either way, it's the same thing. All right. There you go. That's your slope. Now, that's just one slope, right? As h gets smaller and smaller, let's see what happens. So if h was 0.1, right, then the slope would be 46 plus 5 times 0.1. I don't really need my calculator, but I'll do it anyway. It would be 45.5. That's with h being 0.1. And much like the previous examples where we're getting closer and closer, now I have a number that tells me how close I am to it. So now I'm within 1/100th of the value, 4. So I get 45.95. So as h approaches 0, the slope of the tangent line is equal to, let's just call it m, 46. And you can kind of see that right here. As h approaches 0, this term is going to get smaller and smaller and smaller, and your slope is just going to become 46, which means I'm never really going to need to do this ever again. But since I've done it so many times already, I just wanted to show you one last time how plugging in very, very small numbers gives you a sequence of values, just like those lines that I drew, that are getting closer and closer and closer to this value. Okay. So let's formalize that. The slope of the tangent line at x equals a is given by the limit as h approaches 0 of f of a plus h minus f of a all over h. Alrighty. Excuse me. Example, I don't know what we're up to. 6. So f of x is x squared minus 11x plus 10. Find the slope of the tangent line. At x equals 2. Well, now we could just put this entire recipe in there. I like to do it in steps. So let's first do this, because we've done that several times, and then we'll take the limit when we're done. So we got f of a plus h is a plus h squared minus 11a plus h plus 10, which is a squared plus 2ah plus h squared minus 11a minus 11h plus 10. I guess you can call that step 1. All right, figure out what f of a plus h is. All right, step 2. Subtract f of a. That's actually the easy part. F of a is just the same function here, replacing x with a. It's just plugging in whatever a is. Ultimately, a is going to be 2. I'm going to go ahead and wait and plug in the 2 later. If you want to plug it in now, you can. So when you subtract that, you're going to get minus a squared plus 11a and minus 10. So all of these terms are going to cancel out. So that's step 2. So step 3, divide by h. So we take the result of step 1 and 2. So after we've canceled out step 1, step 2, this is the result of step 2. You got 2ah plus h squared minus 11h. Divide everybody by h. It gives you 2a plus h minus 11. Step 4, plug in a. So a was 2. So x equals 2. So that means a is equal to 2. Yeah. X is equal to a. So you get 2 times 2 plus h minus 11. 4 plus h minus 11. Which is h minus, what's that, 7? And then step 5, sorry, take the limit. So limit as h goes to 0 of h minus 7 is 0 minus 7, which is negative 7. So that's the 5-step way to do it. If you like just a 1-step method, then you just take the entire formula. It's messy, but you can do it. You plug everybody in, you plug in the 2, you take the limit, you just do it all at once, and then you cross your fingers and grit your teeth and hope that you get the right result, which is -7. So this is your m. Slope of the tangent line is -7. Well, it's time to change it up a little bit. The most common function you'll see for this particular level of calculus is the parabola. Quadratic functions are very common. And we'll see more of those. They show up quite a lot in the business applications. But we need to diversify our catalog of functions that we can do. So let's do example 7. Let's do a square root function. So find the slope at x equals 3. All right. So let's see. I'm regretting choosing 3, but that's okay. It's out there. So let's go ahead. Step 1. Let's do f of a plus h. That's about it. Doesn't get much better than that. All right. Oh, my 9s and my a's. This is dangerous. So there we go. And make sure I keep them straight. Which one's the 9? Which one's the a? All right, now we're going to subtract f of a. Now, unfortunately, this is not a quadratic. This is a square root function. So we're not going to get a lot of canceling. And I'm regretting my choice of numbers, but that's okay. I could just be careful with the 9s. And then step 3, divide by h. And again, you could have just done all of this at once. And just jumped right to this. This is sort of a step 1, step 2, step 3. Sometimes as you go along, it gets easier. In this particular example, because it's not a quadratic function, it's a square root function, it didn't really get much easier. All right, so I'm going to have to now take the limit. But look where we're at with the limit. The limit as h goes to 0 would be dne. So we're going to use that technique that we learned in chapter 1 of multiplying the numerator and the denominator by the same number. This is a special form of 1. Remember, you just take whatever this sign is and you change it. You keep everything else the same. So this is a special form of 1. It's very messy, but it cleans up nicely. All right. Let's see if I can squeeze it into one more row here. The denominator, I'm just going to write it down now because you don't actually want to do anything with the denominator. You're just going to wait on the bottom. All of your work is going to be in the top. So just going to copy down the denominator and don't do anything with it. So all of my work is going to occur on the top. So when I multiply a square root times a square root, those are going to cancel. And I'm going to get 4a plus 4h plus 9. So the radicals will cancel. In the interest of time and space, I'm not going to show that, but you've seen it before. You have the square root of something times the square root of the same thing. So it's the square root squared, which is just whatever the radicand is. Then you have the outer and the inner. Because one of them is positive and the other one is negative, those are also going to cancel. And again, in the interest of time and space, I'm not going to write that. Then you have a negative times a positive, and these are the same square root, 4a plus 9. That's the last term. So that's going to be 4a plus 9. And you have a minus sign here. So this minus sign is going to distribute. And you're going to get 4a plus 4h plus 9 minus 4a minus 9 all over h times the square root of 4a plus 4h plus 9 plus the square root of 4a plus 9. Now, the 4a, the negative 4a, the positive 9, and the negative 9 are going to cancel. I always get tired of writing this denominator over and over again. In my own notes, when I do something like this, I just write like arg, arg for argument, or sometimes I would write rad for radicand, and I would just write it down to kind of make a note to yourself so that when you know you're going to copy the same thing over and over again, it's much quicker just to write rad, 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 rad. The only thing is you better document what that was because it's very easy to lose track of it. And you'd be going, what was the radical again? I erased it 20 minutes ago. Anyway, I've been writing it each time. So now I'm going to cancel the h's. And I'm going to get 4 over the square root of 4a plus 4h plus 9 plus the square root of 4a plus 9. Finally, I'm on step 5 now. So all of that was the end of step 4. That's a very long step 4, right? It's because the nature of this function was a lot more complicated. So now for step 5, take the limit as h goes to 0. And that will give you your slope. Notice by doing all of that work, when we plug in 0, it's not a problem anymore. It's the same thing we did in chapter 1. When you have division by 0, you can use an algebraic technique to get rid of the division by 0. You still have a 0, but notice it's not going to divide by it anymore. It's just going to make these things match. You have 4a plus 0 plus 9. So you just get 2 copies of the 4a plus 9. Yeah, these things match now. They don't cancel out. They combine together. So this is our slope. There's like an invisible 1 in front of each of these radicals. So when I add them up, it's a 2, not a little 2. It's not an index. It's a coefficient of 2. And that's our slope. I could do one more step, which I will do, which is to simplify this. 2 goes into 4 2 times. So my final slope will be 2 over the square root of 4a plus 9. And remember, it was x equals 3. So there's my A. It's always x equals A. So A is 3. So my actual slope is 2 over the square root of 4 times 3 plus 9, which is 2 over the square root of 21. I'll write that up here nice and big. I'm not going to make you simplify it anymore. It doesn't really get much better than that. I was hoping for a perfect square. Like 25 would have been nice. But once I wrote it down and started driving, I didn't want to turn around and go back and change the problem, because I don't know what's going to happen. You might get lucky and get a nice perfect square. If you do get a perfect square, then go ahead and do one more step. If you don't worry about it. It's fine. I want an exact answer. I don't really want a decimal approximation in this section. Not until we start doing the word problems. Then I might want some decimals. All right, let's do one more of these sort of exhausting ones, and then we'll get back to business. Put the business back into business algebra, business calculus. What am I up to? Example 8? All right, so let's do 4 over x plus 5. Find the slope of the tangent line at x equals -2. Okay. All right, let's do it. So step 1, f of a plus h. So 4 over a plus h plus 5. Doesn't get too exciting. These ones don't really clean up very nicely. So then f of a, 4 over a plus 5. Then subtract these. F of a plus h minus f of a. So 4 over a plus h plus 5 minus 4 over a plus 5. And then finally divide by h. Now in this particular example, I use 2 different forms of division. For the formula for the slope, I just used, divided by h, a fraction version. But over in this version, I like to go old school with it. And you might remember me doing this in chapter 1. I like to write it like that. These mean the same thing. You could say all over h, or you could say divided by h with a off to the side. It's just easier to keep track of everything if my divided by h is just kind of hanging out over there waiting for me. So I got x equals -2. I'm just going to save that. So what do I got? I got 4 over a plus h plus 5 minus 4 over a plus 5 divided by h. And now I'm going to find an LCD. So I'm going to multiply this one by a plus 5. Right, I want these denominators to be the same. And then I'm going to multiply this one by a plus h plus 5. And then after I clean all this up, then I'll take the limit. So I've got 4a plus 20 minus 4a minus 4h minus 20 all over a plus h plus 5 and then a plus 5. So once the denominators have been made to be the same, I just write it one time. And then watch what I do with this division. Old school division. Flip and multiply. So it's going to become 1 over h, and I'm changing it to multiplication. Alrighty, we are almost there. Let's do some canceling here. So I've got 4a, negative 4a. This is very similar to one of the earlier examples. Negative 20, positive 20. So now I've got negative 4h all over a plus h plus 5, a plus 5. And then times 1 over h. So this will be times 1, and this will be times h. Yeah, the 1 multiplies by the numerator, the h multiplies by the denominator. So now I can cancel these h's. And we're ready to take our limit. It's the limit as h goes to 0 of negative 4. It's negative 4 times 1, but that's just negative 4. A plus h plus 5, a plus 5. So that'll be negative 4, a plus 0 plus 5, a plus 5. Which would be negative 4 over a plus 5 squared. Notice these are now identical. A plus 0 plus 5 is the same as a plus 5. So there's my slope. Now remember what a was. A was negative 2. That's over here to the side. I was saving that. So we're going to plug in negative 2. Right here where the a is, or x. A and x are the same thing, right? X is general, like all x's. A is very specific for this particular problem. A is negative 2. So I've got negative 4 over 3 squared, which is negative 4/9. So that's the slope at this particular point. And again, I could have plugged in negative 2 much earlier in the problem, but I guarantee you it would be much messier. So if you think this was messy, there are some times where we do it the other way. In fact, I might do that now just to show you, just to wrap this whole thing up. All right, so we've seen the graphs, sort of going through all the different things. The only thing we didn't do today was tables, although... Did I make a table? I can't remember. It's been so long. Well, when I make a graph and I plot points, that's the same thing as a table of values. So we've seen a graphical and a numeric version of it. We've seen a lot of algebra. So now it's time to put the business back into business calculus. And so remember in the last video, we were talking about revenue, cost, and profit. So a company uses the formula, the function, same thing, P of X is negative 0.2 x squared plus 90x minus 4,900 to determine the profit. When X units are made and sold. So what's wrapped up in this function is the two other functions that I talked about last time, the revenue and the cost. So you have the revenue and you subtract the cost. The revenue is from selling them. The cost is from making them. Even if you are not personally making them, you're paying somebody else to make them. And so that's the cost part of it. All right. You can even use this formula if you're just buying and selling. Find the average rate of change on the interval 64 and 64 plus h. So 64 is the number of units. So x is equal to a. So this is my A units. $64 units, 64 gizmos or gadgets or whatever they are. All right, now this one's very similar to one of the very first examples we did today where it's like a U-shaped graph, although this one's an upside down U like this, if I were to graph it. Probably take me longer to graph it than it would to actually solve this problem. So let's just get right to it. So we've got, now we're just going back to AROC really quickly here. So P of A plus H, that's negative 0.2 A plus H squared plus 90 A plus H minus 4,900. Negative 0.2 a squared plus 2ah plus h squared plus 90a plus 90h minus 4,900. Does that look familiar? Yeah, that's exactly what we were doing earlier, but with larger numbers. Oh, and decimals have just shown up. So I've got negative 0.2 a squared minus 0.4 ah minus 0.2 h squared plus 90a plus 90h minus 4,900. Now we're going to subtract PA, which with these types, it's very easy. You just subtract all of the terms, do the opposite of all of the terms that have an A. Oh, and the constant term as well. So it's this function where you're plugging in A, which is the reason why we make a distinction between A and X, right? X is general. It could be any variable or any value. A is specific to this problem. It's 64. So much less space is going to be taken up here because we can just cancel these out. And this will give us our average rate of change. But we need to divide this by h, the next step. So PA plus H minus PA over H is this divided by H. And I like to divide 3 times. Cancel, 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 cancel. And there we go. That is our AROC. It's not the IROC yet, it's the AROC. It's the average rate of change. Now we need to plug in 64. Right, so sometimes you call this the gen AROC or the general AROC as opposed to the specific AROC where we plug in a value for A. I probably could do that in my head, but I don't want to screw this up, so I'm going to just do it here. 0.4, negative 0.4 times 64 is negative 25.6. And then plus 90. That's a negative, that's a positive, so it'll be positive 64.4 minus 0.2h. So this represents the average rate of change. This is the AROC on the interval 64 plus h. So, as we get closer and closer to 0, let's just write lim. So we take the limit as h approaches 0 of 64.4 minus 0.2h. This is going to become 64.4 minus 0.2 times 0, which is just 64.4. So this is the AROC, instantaneous rate of change. What does this mean? This means that profit is increasing at a rate of $64.40 per unit. And again, it's at that particular time. So remember what all this looks like in the graph. This is like a big curve here. And so basically we're saying at this point, when x is equal to 64, the slope of the tangent line is 64.4. I do want to double check that though. So I've got a 0.4. Just, it's a coincidence that they both have the number 64 in them. So it's 0.4 times 64. Yeah, 25.6. And then plus 90, 64.4. Yeah, I'm not very happy with the result. Again, I just randomly selected the numbers, but the fact that the slope is 64.4 has very little to do with the fact that there were 64 units. It's just a coincidence that those came out to both start with the digit 64, the two-digit number 64. Yeah, not really very happy with the way that came out. I don't want to give the impression that because this was 64, that came out to be 64.4. This could have been a completely different number, and this might have still came out to be 64.4. I could do it for a different A, you know. Say 25, right? Well, then you would put 25 in here because I don't know what you're going to get for your numbers. So just to kind of dispel the illusion here that the 64s have anything to do with each other, you could change the number of units to 25. You are not going to get 25.4 or anything like that. So let's see, if there's 25 units, before I erase this, I have to feel better about the result. So let's say 0.4 times 25 Oh, that's even better. That's negative 10. Remember, the limit goes to 0, so that's plus 90. This is 0. Yeah, 0.2 times 0 is 0. 0 plus 90 is 90. 0 plus 90. So there we go, 80. Much better number. Now it doesn't even look like they're related to each other. So I like that one better. All right. Again, it's the value of A is randomly chosen, so it's not going to matter. You're going to get, in this case, you're going to get 80 minus 0.2h. You're going to take the limit as h goes to 0. So now you just saw the same problem with two different A's. And then this time the profit is increasing at a rate of $80 per unit. I do think it's interesting that when it was 64 for X, that the rate was also 64. But that was just a coincidence, however interesting or not. Well, we have run out of time. So that is instantaneous rate of change, part 2 for the rates of change. We will continue to do this process throughout chapter 2, and we'll see more examples like this. But until then, I'm Dr. Jordan. I'll see you on the internet.